Making those large language models even more awesome, especially when they're dealing with tons of information.
Yeah, think about feeding an LLM like a whole code base,
Oh, wow.
or having it have a conversation that goes on for thousands of tokens.
That's amazing.
That's the potential of what they call long context modeling. But,
Yeah,
there are some dumps in the road.
I bet. So we're diving into a brand new paper for this deep dive,
Okay.
and it's called Native Sparse Attention, Hardware-Aligned and Natively Trainable Sparse Attention.
Wow, what a mouthful.
It is, and it's fresh off the press. It just came out on February 16th, 2025.
Oh, very recent.
The research team is from DeepSeek AR and Peking University,
Okay.
and they're really kind of pushing the boundaries of what LLMs can do.
It sounds like it. So are we going to break down like what the main ideas of this paper are?
We are. We're going to get into all the key ideas and then kind of explore like how this new method, could kind of change the LLM landscape.
Yeah, that's what I'm excited about.
Me too, me too. Well, to get started, maybe we should kind of just define the problem a little bit.
Yeah, so let's start with the core of the problem.
Okay.
The attention mechanism.
Okay.
And this is what makes LLMs able to focus on the really important parts
Okay.
of the input text. But it can get really resource intensive when you have these really long sequences.
Okay, so the longer the text,
Exactly.
the harder it is for the model to focus.
It's like if they're trying to find a single grain of sand
Oh, wow.
on a beach that keeps getting bigger.
Oh, that's a really good analogy. Yeah.
It's really tough to
Yeah.
find that one grain of sand.
Yeah, and the paper points out that when you have these really long contexts, up to 64,000 tokens, that attention calculations can use like a whopping 70 to 80% of the processing time.
Right. You're spending most of your day
Wow.
just figuring out what to focus on.
Yeah.
So you don't have any time.
And no time to actually
Exactly.
do anything with the information.
Precisely. So that's where this idea of sparse attention comes in.
Oh, okay.
And this is, instead of like calculating every single word and how relevant it is to every other word,
Uh-huh.
it tries to find the connections that are really important.
Oh.
So it's kind of like it knows where to look on
Right.
that really big beach.
It's like having a metal detector to find that
Yeah,
grain of sand.
exactly.
So that sounds promising, but
Yeah.
we've seen other attempts at sparse attention before.
Right.
What are some of the shortcomings of previous sparse attention models?
A lot of them
Yeah.
kind of overpromise
Uh-huh.
and then don't really deliver
Okay.
in practice.
All right.
And this paper talks about two big problems. They call it the illusion of efficient inference
Ooh.
and the myth of trainable sparsity.
Okay, unpack those a little for me.
So basically,
Yeah.
some methods, they only achieve sparsity
Oh, okay.
in like one phase.
Okay.
So it might be just in decoding.
Right. So not during the whole process.
Exactly.
Okay.
And then some of them actually aren't compatible with the architectures
Oh, right.
that we use today, like GQA
Okay.
and MQA,
Yeah.
which are designed for efficient memory access.
Got it. Got it. So it seems like we're hitting a wall with these existing methods.
Yeah.
So what makes this new approach, this NSA, different?
So NSA, or natively trainable sparse attention,
Right.
it tackles these problems head on
Okay.
by focusing on
Yeah.
hardware-aligned inference speedup
Okay.
and a training-aware design
Okay.
for the algorithm. So it's kind of like,
So it's thinking about the hardware from the beginning.
exactly, if you train a race car driver on a racetrack
Right.
from day one,
Uh-huh.
they're going to be much better
Yeah.
at racing on that specific racetrack.
Yeah. That makes sense.
They're optimized
Yeah.
for the environment they're in.
Okay, I like that analogy. So how does it work?
Okay, so
Like, let's get into the nitty-gritty a little bit.
let's get into the hood.
Yeah. From what I understand, this NSA, it kind of replaces these
No.
bulky, full key value pairs
Uh-huh.
with a more compact
Yeah.
set of representations.
Yeah, exactly.
They use these terms compressed, selected,
Right.
and sliding window.
Right.
And those are chosen
Right.
based on whatever the query is.
Based on the query, exactly.
So is that kind of right?
That is a great way to visualize it.
Okay, good.
Instead of like keeping track of everything
Yeah.
NSA picks and chooses
Oh,
to be
okay.
more efficient.
it's like
like a
decluttering your mind.
exactly.
Okay, so let's break down those different
Yeah.
representation types.
Okay.
What is token compression?
So token compression is kind of like if you condensed an entire chapter,
Oh, wow.
of a book into a single paragraph
Oh.
that captures like the main points.
Right, the gist.
Exactly.
Okay.
And it does this using these things called learnable MLPs.
Okay.
They're like neural networks.
Okay.
And it uses a method called intra-block position encoding
Oh, right.
to really get that information compressed.
So we're not losing, like, the main idea.
Exactly.
But we're getting rid of
Right.
some of the details.
We're getting rid of the fluff.
Right, exactly. But we don't want to lose all the details, right?
We don't.
So that's where token selection comes in.
Exactly.
So what is token selection?
Token selection is about finding the specific tokens that are crucial
Okay.
for the model to understand the whole context.
Oh, right.
It's like highlighting the key sentences in
Oh.
that single paragraph that we
Right.
talked about before.
Right, right. So it's going
You
even
see-
deeper and
That's
finding the
cute.
really important stuff.
Exactly.
Okay, and then what about that sliding window representation? What is that?
So the sliding window that focuses on the most recent tokens
Okay.
in the sequence,
Okay.
so we don't lose the local context.
Right. So we're thinking big picture and small picture.
Exactly. It's like a short-term memory.
Oh, okay.
And then the other two are
Yeah.
kind of the long-term memory.
Okay, that makes sense. So we have these, we have these three different parts working together.
Yeah.
How do we keep them from interfering with each other?
So to prevent any conflicts,
Yeah.
they actually have independent sets of keys and values.
Okay.
So each branch, like compressed, selected, sliding window,
Uh-huh.
they all have
Yeah.
their own little workspaces.
Okay, that makes sense.
So they're not stepping on each other's toes.
Right, right. So before we move on to the results, I want to touch on that kernel design that they talk about.
Oh, yeah. That's a
Yeah.
little technical,
Yeah.
but
But basically they optimize it for the hardware, right?
they do. So they use this language
Oh.
called Triton to really fine-tune
Yeah.
NSA for the hardware.
So it's making sure that it can run
Exactly.
efficiently on the computers that we have today.
It's all about efficiency.
Okay, and we're going to talk about that efficiency in the results, right?
Absolutely. We're going to see how NSA stacks up against
Yeah.
full attention
Yeah.
and some other sparse attention methods
Okay.
in a ton of different tasks.
All right, I'm ready. Let's get into it.
Let's do it.
All right, so let's talk results. I'm really curious to see how NSA performs in practice. What kind of tests did they run?
They put it through the ringer.
Oh, wow.
They tested it on this massive 27 billion
Wow.
parameter transformer model,
Okay.
and they trained it on a whopping
Wow.
260 billion tokens.
That's crazy. Okay, and what did they find? Did it live up to the hype?
They tested it on a whole range of tasks, like general benchmarks,
Okay.
language understanding and reasoning,
Uh-huh.
long context scenarios,
Okay.
and even this really challenging area called chain of thought reasoning.
Ooh, what is that?
That's where the model has to
Yeah.
think step by step
Okay.
through these complex problems.
Oh, wow.
So it's not just one test. They really
Right.
wanted to see how it performed
Yeah.
across the board.
Yeah, yeah. So how did it do on those general benchmark tests?
So even though NSA is like inherently sparse,
Okay.
meaning it does fewer calculations,
Right.
it actually held its own
Okay.
incredibly well
Okay.
against the full attention model.
So it's doing just as well.
And in some cases, it even outperformed the full attention model.
Wow. So it's actually
Yeah.
better in some cases?
It suggests that you don't necessarily have to sacrifice performance
Right.
for efficiency.
That's what we want.
Exactly.
Were there any specific areas where NSA really knocked it out of the park?
Yeah, it's really interesting. They found that it showed particular strength
Okay.
in tasks that required reasoning.
Oh, okay.
So this suggests that by making the model
Yeah.
be more selective
Okay.
with its attention, it actually gets better
Right.
at zeroing in.
So it's not distracted by all the extra stuff.
Exactly. It's focusing on what's important.
Okay. Yeah, that makes sense. All right. So what about those long context scenarios you were talking about?
So that's where things get really exciting.
Okay.
One of the tests they use is called needle in a haystack.
Oh, wow. Okay.
And they hide this tiny little piece of information
Okay.
in this massive, massive chunk of text.
Right.
Like finding a word
Yeah.
in the giant encyclopedia.
Yeah.
And NSA got perfect accuracy every
Wow.
single time.
Perfect accuracy. How is that possible?
That's the power
Yeah.
of that hierarchical structure.
Okay.
Remember those compressed and selected tokens?
Right.
That lets it quickly scan
Okay.
and then zoom in
Right.
on the relevant part.
So it's got both.
It's got a bird's eye view,
Yeah.
and then it can look.
And a magnifying glass. Okay, cool.
Yeah.
So what about other tests for long context?
Yeah, so they tested it on
Yeah.
Longbench, which is specifically designed
Okay.
to see how well models
Right.
handle these really, really long sequences of text.
Okay.
And once again, NSA came out on top.
It's winning every competition.
Well, it's like an Olympian.
Yeah. It's like Michael Phelps of sparse attention. The paper also mentioned that it excelled in multi-hop question answering and code understanding.
Yeah, those are really complex tasks
Yeah.
because it has to figure out the
I get it.
relationship between different pieces of information
All right.
spread across the text.
Yeah.
So, for example, multi-hop question answering.
Okay.
It's like you have to piece together clues
right.
from multiple sources
Yeah.
to answer a question.
Okay. Yeah.
And code understanding.
Yeah.
It has to decipher
Yeah.
the logic and the connections
Yeah.
within complex code.
Right.
And NSA was able to excel in these areas.
Okay, so we've got faster training, it's better at reasoning, and it handles long contexts really well.
Do.
But we can't forget about the main thing here, which is efficiency, right?
Right. We want to know how fast this thing is.
How much faster is NSA compared to full attention, especially during training?
So they use Triton
Okay.
for both implementations
Okay.
of NSA and full attention.
Uh-huh.
And ran them on this super powerful
Okay.
8 GPU A100 system.
Okay, so it was a fair fight.
It was a fair fight.
They were running on the same...
Same hardware.
Yeah, same hardware. So what did they find?
So they found that NSA was significantly faster, especially as that context
that's
length
exciting.
got longer.
Okay.
For 64K tokens,
Yeah.
they saw a 9x speedup.
Wow.
For the forward pass,
Okay.
and a 6x speedup for the backward pass.
That's amazing. So we're talking about training these huge LLMs
Yeah.
9 times faster.
That's a game changer
That's crazy.
for researchers.
Yeah, like they can experiment more.
They can experiment more.
They can try new things.
Exactly.
Wow. So faster training, but also we need to talk about decoding, right?
Yes, decoding. That's that process of
Yeah.
generating the text.
Okay.
And this is often a bottleneck
Right.
for LLMs.
Okay.
Especially when they have to deal with these long contexts.
Right.
And decoding speed is mostly determined by
Okay.
how fast they can access
Yeah.
and load those key value pairs
All right.
from memory.
So this is where NSA's streamlined design really helps, right?
It really helps because it has fewer things
Yeah.
it needs to load.
Yeah. So what kind of speed up did they see there?
Up to 11.6x
Wow.
for 64K token sequences.
That's incredible.
It's like, you have a high-speed internet connection.
Right.
And you can just stream
Yeah.
HD video without any buffering.
Yeah, no ag. That's what Okay, so NSA is making them faster and more efficient, both in training and decoding.
Yeah.
What are some of the things that they did to make it so efficient? Like, what are the kind of secret sauce elements here?
So one of the key things is that blockwise memory access pattern.
Okay.
Remember we talked about
Yeah.
processing information in chunks?
Yeah.
That really aligns with
Yeah.
how the hardware is designed.
Yeah, it's working with the hardware instead of existing.
Exactly. They also use some clever loop scheduling
Okay.
to optimize the data flow.
Okay, so they've really thought about every aspect of it.
They really have.
But it wasn't always smooth sailing, right? I'm sure there were some challenges along the way.
There were definitely
Yeah.
some hurdles they had to overcome.
What were some of those?
So one of the biggest challenges
Yeah.
was actually figuring out
Uh-huh.
the best way to select those tokens.
Oh, right.
Remember we talked about token selection?
Yeah.
They tried a bunch of different approaches. They
Oh,
even tried
yeah.
adapting existing
Yeah.
sparse attention methods
Right.
for training, and that turned out to
Ah.
be really tricky.
So it wasn't as simple as just taking what was already out there.
No, it wasn't. They had to come
Yeah.
up with something new.
Yeah, okay. Can you give me an example of like a specific challenge they had to overcome?
They looked into using these clustering methods
Okay.
for token selection.
Okay.
It seemed really promising at first,
Okay.
but it was computationally expensive
Right.
and really hard to optimize.
Yeah. Yeah.
Especially when you're working with these
Yeah.
really complex architectures
Sure,
like
yeah.
Mo models.
Right.
They also tried
Yeah.
other blockwise
Yeah.
selection strategies,
Okay.
but a lot of them relied on
Yeah.
these non-differentiable operations,
Okay.
which made it hard for the model to actually why.
Yeah, it's got to be trainable.
It does.
Yeah. Okay, so it sounds like these early challenges really helped them figure out the best way to design NSA.
They did.
Okay. And did they get any insights from anywhere else?
So they got some really valuable insights
Okay.
from visualizing the attention maps
Okay.
of their full attention model.
Okay.
And they saw this really interesting pattern.
What's that?
Attention scores.
Okay.
They tend to cluster together
Okay.
in blocks.
What do you mean by that?
So imagine you're reading through a text
Okay.
and you highlight
Yeah.
the important words or phrases.
Yeah.
You'll probably notice that those highlighted sections,
Right.
they appear in groups.
Oh, okay.
Right.
So it's not just randomly scattered.
It's not random, it's clustered.
Okay.
And that's exactly
Yeah.
what they saw in the attention maps.
Okay.
So certain parts of the text
Right.
naturally attract
Yeah.
more attention.
Okay.
And this finding actually supports
Okay.
NSA's blockwise
Right.
selection strategy.
It's like they discovered a hidden pattern
They did.
and then used that to design NSA.
Exactly.
That's so cool. So NSA is a big leap forward, right, for long context modeling.
It is.
What are some of the exciting research directions that you think will come out of this work?
Well, one area that's really exciting is
Yeah.
how NSA's efficiency
Okay.
could influence
Yeah.
LLM applications,
Okay.
especially ones that require that
Yeah.
complex reasoning and long-range connections
Right.
within the text.
Can you give me some specific examples? Like, what kind of applications are we talking about?
So imagine LLMs
Yeah.
that can
Yeah.
analyze and understand
Yeah.
these dense legal documents
Okay.
or these really complicated scientific papers
Okay.
or chatbots
Yeah.
that can have
Yeah.
more natural and
Yeah.
nuanced
Right.
conversations
Yeah.
and remember details
Right.
from earlier interactions.
Right. That would be awesome.
We might even see new
Yeah.
types of creative writing tools
Oh, wow.
that can help authors
Oh, wow.
that write more compelling stories
Right.
with intricate plot lines
Oh.
and character
I feel
development.
it's going to change the way we use LLMs.
It's going to open a whole new
Yeah.
world of possibilities.
Yeah. Okay,
But
so...
there's one more aspect of efficiency
Okay.
that we haven't really touched on,
Okay.
and that's decoding speed.
Right. We talked about it a little bit at the beginning.
I did.
Yeah.
That's that process of
Yeah.
generating text.
Okay.
And it can be a real bottleneck for LLMs,
Okay.
especially when they're working with those
Yeah.
long contexts.
Right.
Right? So decoding speed is all about how quickly the LLM can actually generate text after it's processed all that input.
Right. Right.
And this is where NSA's efficiency really comes into play.
Okay. Yeah.
Remember how we talked about how it reduces the number of tokens that need to be loaded from memory?
Yeah. Yeah.
Well, that directly translates
Okay.
to faster decoding speeds.
So it's not just training them faster, it's making them faster.
It's about making them more responsive
Yeah, more responsive.
when you're actually using them.
Right.
So you ask it a question,
Yeah.
it can answer much
Right.
more quickly.
Yeah, so it's like a more natural conversation.
Exactly.
Instead of waiting, 5 minutes for it to think.
Exactly.
Okay, so what kind of speed improvements did they see in the decoding process?
They saw speedups of up to 11.6x.
Yeah.
Compared to traditional full attention.
So that's huge.
Especially when you're working with those longer sequences.
Okay, so that means, quicker analysis of
Yes.
documents, more seamless.
A better user experience.
Yeah, exactly.
It makes LLMs more practical.
More usable.
For everyday use.
Yeah, yeah. I'm starting to see how NSA is more than just like a small improvement.
Right.
It's a potential game changer.
It is. It has the potential to revolutionize
Yeah.
how we interact with LLMs.
Yeah, it's like opening up all these new possibilities. This has been a really cool deep dive, I think. We started with those challenges, long context modeling,
Yeah.
and we saw the limitations of existing methods, and now we've arrived at this really cool breakthrough
And here we are.
with NSA. It's like we've seen like the evolution
It's a big step.
of LLMs happening right in front of us.
It really shows how smart these researchers are.
Yeah.
Constantly pushing the boundaries
Yeah.
of what's possible with AI.
Yeah. So as we kind of wrap up this deep dive, what's like the one key takeaway you want our listeners to remember about NSA?
I think the biggest thing is that NSA allows us to move beyond the limitations of those traditional attention mechanisms.
Okay.
It's making way for these more efficient, powerful, and accessible LLMs.
So it's going to change everything
It'll be
about how we use LLMs.
It's a big development, for sure.
Awesome. Well, that concludes our deep dive into NSA. Thanks for joining us, everyone, and be sure to subscribe.
And stay tuned
For
for the next deep dive.